Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, WA campus. The slides that have been used in this lecture have been edited from the two sources given here. The topic of this lecture is control transfer instructions. Control transfer instructions is the sixth type of instructions in the instruction set of 8086 microprocessor. Control transfer instructions are available in 8086 and above microprocessors, but in this lecture most of the time we would refer to the instruction setup or control transfer instructions used in 8086 and 8088 microprocessor. Control transfer instructions allows a programmer to skip a section of the program or set of instructions and to branch to any other part of the memory or the code segment for the next instruction to be executed. So normally microprocessor executes instructions of the program in a sequential pattern. One instruction is executed after the other and the next instruction is then executed. The next instruction is the one that happens to be the next in the program. But control transfer instructions disturb the sequential flow of execution and instead it allows the program control to jump to another place in the program and to execute instructions from a different part of the program while skipping instructions that would otherwise be executed if followed a sequential pattern. The conditional jump instruction allows to take decisions based upon the numerical tests performed by compare and test instructions. The results of these numerical tests are held in the flag bits, and then these flag bits are then tested by conditional jump instructions, and the jump is whether the jump is taken or not taken, depending on the condition checked. Loop and conditional loop are also forms of jump instructions. Control transfer instructions are categorized in two groups, conditional jump instruction and unconditional jump instruction. Unconditional jump instructions would cause the flow of control to another place in the program without checking any condition, but a conditional jump instruction always check for a condition. If that is satisfied, the jump will happen, and if the condition is not satisfied, the jump will not happen. In case of unconditional jump instructions, these instructions are represented with JMP, and there are three types of unconditional jump instruction. The mnemonic or the name of the instruction is always JMP used in programming. But still there are three types: short jump, near jump, and far jump. And all of these jumps are categorized depending on the range of the jump, depending on the number of bytes that are skipped from the current place or the current address and the next target address. So in case of short jump, the number of bytes that are skipped our range is from plus 127 till minus 128. So the jump can happen in the forward direction or it can happen in the backward direction. So plus 127 is the maximum number of bytes in the forward direction, and minus 128 or 128 is the number of maximum bytes that can be skipped in the backward direction. So short jump is a 2-byte instruction with 1 byte is the opcode, that is E8 normally. E8 in hexadecimal is the operation code of the short jump, while assigned displacement that follows the opcode represent the number of bytes that would be skipped, and that is called the displacement. So that is a signed number, and that signed number represent a value from plus 127 till minus 128. So if the value is negative, then the jump is in the backward direction, and if the value or the displacement is positive, the jump is in the forward direction. And always the jump happens from the address following the jump. So whenever the jump instruction is being executed, an instruction pointer, which is a register inside the microprocessor, stores the address of the next instruction which follows the jump instruction. But this jump instruction would cause the jump to a different place in the program instead of executing the instruction that is pointed to by the current value of the instruction pointer. A 3-byte near jump, which is slightly larger jump than the short jump, is a 3-byte jump. Near jump is a 3-byte jump. This allows a branch or jump within plus minus 32 kilobytes from the instruction in the current code segment. So when this near jump is being executed, it has a 2-byte signed displacement, and this 2-byte or 16-bit signed displacement provides the jump in the backward direction for 32 kilobytes, or in the upward direction for 32 kilobytes. So that's why plus minus 32 kilo is used for the complete range of this near jump. So this near jump allows a jump to anywhere in the code segment, in the existing code segment, while the short jump allows the jump either 127 in the forward direction or minus 128 in the backward direction. There is a 5-byte par jump as well that allows a jump to any memory location within the real memory system. So the short and near jumps are often called intra-segment because always these jumps would cause the flow of control within the same segment, while the far jump, which is a 5-byte jump, this allows a jump from one segment to the other segment. And that's why far jumps are also called inter-segment jumps, because this jump is happening between the two segments. Far jump, the 5-byte far jump obtains a new segment and offset address to accomplish the jump. The first byte of this far jump is the opcode, which is EAH. E8 is the opcode for short, E9 is the opcode for near jump, and EAH is the opcode for far jump. The next two bytes, bytes 2 and 3 of this 5-byte instruction, contain the new offset address, which is the content of the new content of the instruction pointer, which points to the next instruction or provides the offset address for the next instruction, while the last two bytes, bytes 4 and 5, contain the new segment address, which would be loaded to the code segment register. And so these 4 bytes provides 2 bytes are the new content of the instruction pointer, 2 bytes are the new content of the code segment. In case of protected mode, the segment address taken from the above 5-byte far jump would access a descriptor, and that descriptor would then describe the segment to where the jump will happen, just like the addressing in the protected mode. This is a very simple example where the memory is shown with some addresses, and let's assume that the jump happens between these locations, where 1000 is the current location where the jump instruction is stored. So the jump is a 5-byte instruction, so this is the first byte is the opcode, and memory, actually the EA would be stored in the binary form, but for simplification JMP which is the mnemonic of this instruction, is used here. The next 2 bytes read as 0, 1 to 7 would provide the new content for the instruction pointer and or the offset address for the next instruction. The last two bytes provides the content of code segment, which would be read as a 300. So this 16-bit value is the new content of code segment, and while this instruction is being executed, the instruction pointer points to this instruction, which is stored at 1004. But this instruction, which is the far jump instruction, would cause the control to flow from this, instead of this location, to the location here. And how this jump happens, the address of this jump is calculated or computed as follows. The instruction pointer, these two bytes would provide the new content of the instruction pointer. 0127 is the new content of the instruction pointer. 8300 is the new content of the code segment. So 10 is appended at the right side to make it 20 bit value. So 83000 would be the starting address of the next code segment, which is defined somewhere here. And then this offset address, which is the new content of the instruction pointer, is added with this starting address, which is 8300 and an additional 0. This 127 is added, so it would give us 83127 as the new physical address. And this is the address of the next instruction to be executed. So this instruction would cause the next instruction to be executed from here, not from here. If this instruction would not be a jump instruction, then the microprocessor would go in a sequential pattern and the next instruction would be executed from here. But instead, this jump instruction causes the next instruction to be fetched from a different code segment, and the location of that code segment is here. So this is a far jump. Okay, so conditional jumps are always short jumps in 8086 and 80286. The limit up or the range of short jump is within plus 127 and minus 128 bytes from the location following the conditional jump. In later microprocessors, 80386 and above, conditional jumps are either short or near jumps, and the range of these jumps is plus minus 32 kilo, which covers the entire code segment. So just like the near jump, unconditional near jump. In 64-bit mode of the Pentium 4 computers, the near jump distance is plus minus 2G for the conditional jumps, because the segments in the segments can be 4 gigabyte segments, as happens to be in the protected mode. So in the protected mode, the segment can be 4 gigabytes, and in that case, the jump range is plus minus 2G to cover the entire segment of 4 gigabytes. It allows a conditional jump to any location within the current code segment. So in case of these jumps, the range is plus minus 32 kilo, or in case of Pentium 4 operated in 64-bit mode, the range is plus minus 2G. So in both of these cases, the entire segment is covered. Even if the segment is 64 kilobyte is here, or if the segment is 4 gigabyte is here. So in both cases, the entire segment is covered. Conditional jumps instructions take decisions based on testing some flags, and these flags are sign flag, zero flag, carry flag, parity flag, and overflow flag. So these are the 5 flags that are normally tested for taking decisions. If the condition under test is true, a branch to the label associated with the jump instruction occurs, and if false, next sequential step in program executes. For example, a jump with carry, JC, is a conditional jump instruction, and when this instruction is executed, the jump will happen if the carry bit is set, otherwise the jump will not happen. Most conditional jump instructions are strike forward, as they often test 1 flag bits, just like jump carry. Although some test more than 1 flag bits, we will see some examples shortly. Because signed and unsigned numbers are used in programming, and when they are used, signed and unsigned numbers are sometimes compared with each other, and based on the result of their comparison, conditional jumps instructions are executed. So as signed and unsigned numbers are compared in programming, there are two sets of conditional jump instructions for magnitude comparisons, and then there are in 8086 microprocessor, there are signed conditional branch instructions normally used for comparing signed numbers, and similarly there are unsigned conditional branch instructions. And both of these types of conditional branch instructions, they check flags. If the conditions are true, the program control is transferred to the new memory location in the same segment by modifying the content of instruction pointer. Normally, the set of instructions used for the signed conditional branch instructions are given here. For example, these are the names of the conditional branch instructions, and there are some alternatives used for these instructions as well. For example, jump JE, and there is a displacement, so jump F equal. So it checks, it tests if the computations performed earlier, if the two values were equal or not, and if they are equal, the condition must be stored somewhere in the flags, normally in the 0 flag, and sometime in more than one flags. So if the equality condition is satisfied, and that satisfaction is checked inside the flags. So if the result or the values are equal, the jump will happen to this offset address. This is a displacement, 8-bit displacement that identifies the next location within the current segment. So jump F equal, and the alternative of this jump instruction is jump F0. So as the name indicates, if two values are compared with each other and the result is 0, so in comparison normally one value is subtracted from the other. So if the two values are equal, then the result would be 0, and that would be stored in the 0 flag. So if the 0 flag is 1, the jump will happen, and in other words, jump if result is 0. So if the result is 0, or if the value of the Z flag is 1, if the result is 0, then obviously it will set the Z flag. So if the 0 flag is 1, it will jump to the displacement. So jump if result is 0. And similarly, jump if not equal, J and E, jump if not equal. So the jump will happen if the result, the two values are not equal to each other, and this is the offset address to where the jump will happen. So jump F not equal, and the alternative of this jump instruction is jump F not 0. Jump F not 0, it will again check if the Z flag is 1 or 0. So jump F not 0 means that the result of the comparison is not 0, and if the result of comparison or subtraction is not 0, then that would mean the Z flag is 0. So this jump will happen if the Z flag is 0, and in other words, jump if not 0. Similarly, jump if greater, if the two values are compared and one is greater than the other, then the jump will happen, jump if greater, and jump if not less than equal. So they're the same, but in different words. So jump if not less or equal, the jump will happen to this displacement provided. Similarly, jump if greater than or equal, as the name indicates, jump if greater than equal, jump if not less, and jump if less than, JL jump if less than, jump if not less than. Similarly, if JLE means jump if less than or equal, so the jump will happen if this condition less than or equal is satisfied. And finally there is JNG, jump if not greater, jump if not greater than, and the condition is satisfied, the jump will happen to this displacement. And when unsigned numbers are compared, normally the jump that are normally used after unsigned numbers are compared, this is the setup jumps instruction that should be used when unsigned numbers are compared. So they're not that much different. Some of them are common. For example, jump if equal, it's there as well, and jump if 0 is also there. Jump if not equal, it's there. Jump if not 0 is there. Jump if above is not here. So jump if above, if one value is greater than the other, uh, jump if above instruction should be used. Jump if not below or equal. So N means not, B means below, E means equal. So jump if not below or equal. And similarly, jump would happen if jump if above or equal. So it's also not there. Jump if not below, this instruction is also not there. Jump if below, jump if not above or below, jump if not above or equal, jump if below or equal. So these instructions are not here, and these are the alternative name of these instructions. So either of these instructions could be used when unsigned numbers are compared with each other. Okay, so there are other instructions as well, conditional instructions that test individual flag bits, such as overflow and parity flags. In 8086, conditional branch instructions affecting individual flags are here. So this is a set of instructions with mnemonics and a short explanation, and these instructions are testing a single flag. We will see some examples of conditional control transfer instructions that are checking more than one flag shortly. So these instructions, process control control transfer instructions or jump instructions, uh, uh, check a single flag. For example, jump if carry, jump if the carry flag is 1, then the jump will happen to this address. If not, then the jump will not happen. Similarly, JNC means jump if no carry, or jump if the carry, it will jump if the carry flag is 0. So remember that jump if no carry means that the carry is not set. So it will jump if the carry flag is 0. Similarly, jump if parity, in this flag, this condition or this jump test the parity flag, jump if parity. So if the parity flag is 1, the jump will happen, otherwise the jump will not happen. And for the parity, there is a JNP, that means jump if no parity. So this instruction will cause the jump if the parity flag is 0. And similarly, there are two instructions for overflow. Jump if overflow. So if the overflow flag is 1, it will cause the jump. If the overflow flag is not set, so jump if no overflow. So if the overflow flag is 0, the jump will happen. And overflow occurs when, for example, when two values when a larger value is stored in a smaller register, so in that case overflow happens. Similarly, jump if sign, it checks the sign flag. Jump if sign, jump if the sign flag is 1, and jump if no sign. So this condition, this instruction checks if the sign flag is 0. So the jump will only happen if the sign flag is 0. And similarly, JZ, jump if 0, if the result is 0 or the Z flag is 1. If the result is 0, then it will set the Z flag to 1. And similarly, for the 0 flag, there is another instruction, JNZ, jump if result is not 0. If the result is not 0, the result of previous computation is not 0, then Z flag would be 0. This is a typo, so this will jump if Z flag is 0. Okay, so here is the conditional jump instruction, complete set of jump instruction, conditional jump instructions. The alternate are not mentioned here, but here we have the assembly language instructions, and here we have in this column we see the flags that these instructions test, and here is a small explanation of the operation that these instructions perform. So jump if above instruction checks if 0 flag is 0 and if the carry flag is also 0. So this instruction checks these two flags. Jump if above or equal checks if the carry flag is 0, and jump if below checks only the carry flag, but jump if below or equal checks both 0 flag and the carry flag. Jump if carry test only the carry flag. If it is 1, then it jumps, or if it is 0, then it doesn't jump. Jump if equal or jump if 0, these are the two alternatives of each other. So both of these instructions check the Z flag only. But if jump if JG, which is jump if greater than, checks two flags. Jump if greater than equal checks only the sign flag. Jump if less than checks only the sign flag. And if it is not 0 or if it is 1, then it would jump. If jump if less than or equal checks the two flags, Z flag and the sign flag. J and C, jump if no carry checks the carry flag only, and jump if not equal or jump if not 0 checks only the 0 flag. Understanding these instructions is a bit confusing. Jump if not equal or jump if not 0, jump if not 0, or jump if the result is not 0, and the result is not 0 means that the 0 flag has not been set. The 0 flag is set to 1 only when the computation result is 0. So when Z is equal to 0, that means that the result the values that were compared are not equal to each other, or their comparison or their subtraction didn't give 0. So that's why the 0 flag is still 0. If it would have given a 0 value, then the Z flag would be set to 1. Okay, so jump if no overflow, jump if no sign, jump if no parity, jump if parity or overflow, jump if overflow, jump if parity or equal, jump if sign, jump. Okay, so the two the instructions highlighted here, these jumps check flags, one flag or more than one flag, but the later instructions, the last three instructions, are different than these jump instructions, in the sense that these instructions look for the value in the counter register. So jump if CX is 0, if the value in CX is 0, so this is a counter. Normally this is used in many other string manipulation instructions as well, and for example with repeat prefix, and also there are conditional, this counter is used with conditional jump instruction like JCXZ. So this instruction checks if the value of counter CX register is 0 or not. So if it is 0, this jump will happen. And here there is a 32-bit version of the instruction as well that checks the extended version of the counter register ECX. So jump if ECX is 0, jump if RCX is 0. So obviously CX is available only in 8086 and 8088 microprocessor. So this instruction can only be executed in the 8086 and 8088 microprocessor. ECX is not available in 8086, so in 803886 and above microprocessor can execute this instruction, while this instruction is available in Pentium computer because they have the 64, they can operate in 64-bit mode. So these are conditional jump instructions. They are checking either flag or more than one flag bits, or these are some of the instructions that check the counter register.